Hi, my name is Pop. I am making a video tutorial in Ubuntu Basics and Spreadsheet Basics discussing the Pythagorean theorem. And I'm going to pose the question, how far can you see? I'm going to be using LibreOffice.org's Impress presentation program, very similar to PowerPoint. And I'm also going to be using a calculator and also a spreadsheet. This is Pythagoras, and he discovered this principle, and we use it every day. We use it for surveying, how to get an alignment on a car, everything. How far can you see when you are standing up looking at the horizon? How far can you see while in a 19th century sailing ship's crow's nest? Very often the kid would yell, "Land ho!" or "Thar she blows" when he saw whales. How far can you see in an airplane to avoid a thunderstorm? And then last, I'm going to pose an interesting question. When you are standing up on the moon, how far can you see compared to how far you can see on the Earth? The moon has a smaller diameter. It's a surprising answer. I'm going to show how to use the Pythagorean theorem using a calculator, spreadsheet, some square floor tiles, and then some rectangular floor tiles. And when you're done with this video, you'll be able to calculate the length of one side of a right triangle when you know the lengths of the other two sides. You'll be able to say exactly how far you can see to the horizon if you know how high up in the air you are, whether you're standing up in a crow's nest, in an airplane, or even on the moon. I'm going to quickly go through a traditional explanation which may not be clear to you. Then I'm going to explain it again using floor tiles, which I hope is easier to understand. If you've got a triangle with a 90-degree angle, you can calculate the length of one of the sides if you know the length of the other two. Because if you multiply each side by itself, that is to say, squaring that length, you can derive the length of the unknown side from this formula. A square plus B square. Adding together those two areas gives you the area of C square. If you look at the right triangle closely, you can see that C is the longest side. A is the shortest side. And B is longer than A, but you can see it's a little bit shorter than C. And the figure does not show it exactly, but the angle between A and B, right here, is exactly 90 degrees. Quite often you'll see a little square drawn inside that angle. A triangle with 90 degrees is called a right triangle. If you have a right triangle, then the longest side is always opposite the right angle. If the right angle is in this corner, the longest side is always going to be opposite. In this case, the right angle is at the intersection of A and B. Therefore, the long side is C in this case. The longest side of a right triangle is always opposite the right angle. Side C is the longest side, and it is just opposite of the right angle AB. The longest side of a right triangle is called the hypotenuse. Side C is the hypotenuse. C is opposite AB. There are a couple of things that are worth pointing out. When you add up the three interior angles of any triangle, no matter what the exact shape of the triangle, those three angles always equal 180 degrees. This is always the case, no matter how short or long any of the three sides are, or whatever the angles are. It's always 180. The three angles always add up to 180, even if the triangle does not have a 90-degree right angle somewhere. No matter what the triangle shape, no matter what the length of any of the sides, the angles always add up to 180. There's something else. Sides A and B could be the same length, exactly. If the intersection of A and B is a right angle, and if A and B are the same length, then C will always be longer than the other two sides, even if A and B are of the exact same length. Now here's an example of that. Now you think that Pythagoras was the smart guy, but he had a brother, and his brother was Billy Bubba, and Billy Bubba got straight up rich putting down floor tiles, and that's the way it goes. That's the way life is. The very cerebral Pythagoras, he went to school and he studied arithmetic and mathematics and geometry, and he devoted himself to, quote, non-practical things. As it turns out, the practical aspect of what he discovered far overshadowed the academic side. So, here is a square floor tile. It's 12 inches by 12 inches. Each corner is 90 degrees. And one day they are together, Billy Bubba and Pythagoras asks his brother, "Hey, how long would that diagonal be?" And the brother says, "I don't know. 12, well, let's see, the side's 12, 14, 15, 16, 17 inches. I don't know. Let's just go get a ruler and measure it." But Pythagoras, he wanted to calculate ahead of time. So he took his marker and drew a diagonal. How long is that diagonal? Well, now you've got two triangles, right? And you can arbitrarily name them A, B, and C, the sides. Call the long diagonal C, and A and B are the same length. And there's a 90-degree triangle, right? I mean, if you look right here, this is 90 degrees right there. And C, this diagonal, we're going to call that the hypotenuse, right? Now, if you measure A and B with a ruler, you'll see they're both 12 inches. They're of equal length. The angles are also of equal amount if you measure them with a protractor. We could call this BC, and we could call this AC, and they're both 45 degrees because this is 90, 90, 45, 45. Now, you can visually demonstrate the Pythagorean theorem by adding a few more tiles. This tile represents the B side. I'll call this B. And we're going to multiply B times B, 12 times 12, or 1 foot by 1 foot, and we're visually representing that abstract figure with another square. Throw in another one. Okay. Let's start throwing down the other ones. And it's not quite so obvious. This may not jump out at you, but watch what happens when I start bisecting those tiles. Can you see the square now? Let me remove the superfluous areas. You can actually see the square that was created. This square is next to the hypotenuse. This is the hypotenuse. The smaller squares are on side A and B. And then this big square now is next to the hypotenuse. In case you got lost, I'm going to color the triangle we're talking about. And this is a right triangle. There's a little square in the corner. The top square is an area which is 1 foot square, and you can express it in inches too, multiplying 12 by 12. And by convention, the superscript 2 indicates that 144 is not a mere linear measurement, but rather means an area of 144 square inches. The other square also has 144 square inches, and mentally you can add these numbers and see that the two small squares take up 288 square inches. Now, pay attention to the new segmented square at the hypotenuse. Each triangle is exactly half a 1 foot square. If a whole 1 foot square is 144 square inches, then half of a 1 foot square must be half of 144. So each triangle is equal to 72 square inches. Two of these triangles equal 1 square foot because 72 plus 72 is 144. Also, you can rearrange the triangles in your head and see how two of them make up 1 square foot. When you add up all four, you get 288, and 288 is the same number as when you add up the two little squares. The area of the square of the hypotenuse equals the area of the square of the other two sides, and usually it is expressed in a compressed fashion. A square plus B square equals C square. Now, a new topic. Now you've got a triangle whose sides are not equal, not made from a square. If you are a skeptic, you probably are asking yourself if this concept works all the time for every right triangle. So I'm going to try to visually represent this with floor tiles. I'm going to alter the dimensions so that both sides are not exactly the same. This figure is 2 squares long. In other words, it's 2 feet long and 1 foot down. You can buy tiles of any size. I'm going to square the long length by inserting 2 more tiles. Mentally, I want you to isolate the top 2 rectangles in your mind's eye and consider them as a square above the first rectangle. And I'm going to cut away the excess material so that you can see the actual triangle we're talking about. Now I'm going to square the short side. So far so good. You with me? Remember, this is a right triangle, one which has a 90-degree angle. The little square in the corner, by convention, means that the angle is exactly at right angles. And remember what we're doing. The length of the top line of the triangle, when multiplied by itself, can be represented visually or numerically. In this case, I am representing it visually by drawing in a square. The picture of the big green square is nothing more than the product of the top line of the triangle multiplied by itself. The top line of the triangle is 2 feet long. Each side of that new great big square is 2 feet long, and the square is 2 by 2 feet in area. In other words, 4 feet square. The small square to the right is the product of the triangle's shortest side multiplied by itself. The side is 1 foot long, 1 by 1. 1 times 1 is just 1. And let's count them up. We're going to add up all these new areas. Each tile is a square foot, and there are 5 tiles, so that's 5 square feet, right? Now remember what we're doing. The Pythagorean theorem says that all this stuff, the area we have delineated so far, is equal to the area of the square of the hippopotamus. The word is not hard to remember. You already know hypo, meaning under, and dermic, meaning skin. A hypodermic needle is a needle that goes under the skin. And this is hypo, under, and tenus, like tension. It's stretched under. Well, it's a little hard to remember. Hypotenuse. So let's do it just like the way we did it with the last example, using a right triangle, both of whose sides were equal. Now we're doing it with a right triangle. One side is twice as long as the other side. And I want to show you how hard this is to do. It doesn't work visually all the time so easily. It worked well with the square, but this is a rectangle. And the point of this is that numerical squaring always works. Using arithmetic and algebra and multiplication, squaring and square roots, that always works. A picture is hard to do. In the real world of laying tiles, it doesn't come out, and I'm going to show you. Well, here's 4 of the 5 in place. Now, I got to make a single square out of all of this. And I'll begin by tilting the big square into the hypotenuse. So far, so good. Easy peasy. This is so easy. Almost done. Now all I got to do is the little square, and I have to put that along the sides, correct? I'll tilt it. I think I have to break it up into chunks. What should I do? Break it up into fourths? One piece is going to go here. But let me break it up into chunks, and then I'll rearrange those 4 chunks. Alright, here we go. There's one. Moving them around. And guess what? It doesn't work. There's going to be an amount left over. It's very hard to see. Let me zoom in. Do you see how that sticks out just a smidgen right there? It's too big. And if you went down here, even if you got these lined up perfectly, there would be a place missing right there, wouldn't there? The square root of 5 is the length of the hypotenuse. Numerically, that's the length. But in the practical world of tiles, it's difficult to graphically represent this. Squaring, then adding together the 2 sides, then deriving the square root always works. So, I guess it's time to bring up square roots. The length of the top line of the triangle is 2 feet, and the length of the right-hand side of the triangle is 1 foot, but we already knew those measurements. And the Pythagorean theorem lets us calculate the length of the hypotenuse by kind of like working backwards. We're backing into it. We're saying 2 squared plus 1 squared equals the length of the hypotenuse squared. So that's the same thing as saying 4 plus 1 equals 5. Now all we need is the square root of 5. In other words, we need some number that we represent with a question mark, which when multiplied by itself will equal to 5. And to say it another way, whatever times whatever equals 5. And the technique for figuring out how to get a square root of a number is a completely separate issue. The ability to make use of the Pythagorean theorem is dependent on this other separate skill. And the square roots of some numbers kind of jump out at you. You can easily see, for instance, that in the problem of whatever times whatever equals 9, that the unknown, the question mark, it's going to be 3. 3 times 3 is 9. And in this example, the answer is a regular even number. But with our present example using 5, the answer is not going to be regular, because 2 times 2 is 4. That's too small. 3 times 3 is 9. That's too big. It's somewhere in between. You can do this by hand, and it is laborious, and the skill of calculating square roots is a basic math skill that you should learn. But for this video, we're just going to use a calculator. Now, let me get the calculator up here. You see this? This is the square root symbol, and it's right next to the square symbol. They put them together very logically on a basic calculator. To be sure, you hardly ever use this. I mean, in everyday stuff, you're just adding, subtracting, multiplying, and dividing. So this might be new to you. If you have a number showing on the screen, that number will multiply by itself if you tap the x squared key, then tap equals. So I got a number up on the screen too. I'm going to tap the squared key. Oops, I did it wrong. Pardon me. Let's put 2 up there. Now I'm going to tap this. See how it's squared? Now I'm going to hit equals. 2 times 2 is 4. Let's just go 4 squared. 4 times 4 is 16. If you have a number showing in the screen, the square root of that number will appear if you place the square root symbol in front of the number showing, then tap equals. I'll say it again for emphasis. You got to put that symbol in front of the number. Let me show you. It screws up otherwise. You see I got a 16 up there, and we want the square root of that, so whatever times whatever equals 16. Well, you know it's 4. But watch what happens if I try doing it here. And I put the symbol after. See, it says it doesn't work. So what you got to do is you got to left, now put it in front of, and now hit equals, and it gives you 4. Let's calculate our 5. What is the length of that hypotenuse? 2.236 inches. Interesting. Look at that. You can figure this stuff out using a calculator faster than you can measure it with a tape measure. And that's what surveying is. I come out of the car repair industry. I am retired. And we did front-end alignments. The alignment machine costs $50,000 or $75,000, and the repair guy lives at your shop. And if he's not fixing the machine, he's selling you updates. And of course, you've got to pass that along to the customer. However, For $500 you can buy an alignment machine that works just as good, does not even use a 9-volt battery. It just uses a protractor and some strings, and its accuracy is down to 1/100th of 1 degree. Well, think about it. You can use this to a far greater extent than one would think. There was a guy called Aristarchus of Samos who proposed the heliocentric solar system, and Eratosthenes figured out that the sun was 90 million miles from the Earth. He was certainly within about 5% accuracy, and he did this with a string and a plumb bob and a shadow from the sun. And I may show how to do that in a later video. Well, let's get back to the story here. If A and B are the same length, and if the angle between A and B is 90, then the angles BC and AC are both 45 degrees because all three angles add up to 180. A right triangle which has two sides of equal length is called isosceles. Hard to spell. In our case, we'll be dealing with a triangle that is nearly isosceles in shape. In fact, our triangle is so long and skinny it's just a sliver. Visualize the Earth as a circle whose diameter is 8,000 miles. A line through the Earth is its diameter. Half that distance is the radius. The radius of the Earth is a line drawn from the center of the Earth to any point on its surface. Or, another way to express that would be to say a line beginning anywhere on the surface drawn straight down to the center. If you do begin on the surface and do not go straight down, you won't hit the center. If you went down at an angle, you would miss the center. And the Earth's radius is 4,000 miles. A line touching the Earth is tangential to the radius. Where they meet is a 90-degree angle, always, in every case. Think about it. You can draw a straight line touching the Earth's surface anywhere on the Earth, but the single point at which it touches the Earth is always the point at which there is a right angle to the center. Now, let's get to the problem of how far you can see. Let's say you're standing up and your eyes are approximately 6 feet above the ground. From that height, you can see the horizon. And the higher you are, the further you can see. The distance you can see is the shortest line. It is a mere 3 miles. In relation to the 4,000 miles to the center of the Earth, it's nearly nothing, but the length of the distance of your eyes to the center of the Earth is longer than the distance of the surface of the Earth to its center. The distance from the surface to the center is exactly equal to the radius, but the hypotenuse, the longest length, is equal to the radius plus your height. Your eyes are looking at the horizon. The line from eye to horizon is tangential to the surface. It is a straight line touching the Earth's surface going to your eye. The radius and the tangential line make an exact 90-degree angle. And your line of sight is not tangential when you are looking at the horizon. Your line of sight when you're looking at the horizon forces you to look downwards to the ground, albeit at a very slight angle. If you were higher, you could see further. This is a different triangle. The hypotenuse is longer because one of the components of length has increased. The hypotenuse consists of the Earth's radius plus the height of your eye. If you are in an airplane, the eye is now 600 feet instead of 6 feet. And of course, it is readily apparent that you are looking down at the horizon when you are looking at it from an airplane. No matter how high you are in a plane, the point on the horizon at which you are looking always makes a right angle with the radius because the line of sight is always going to be tangential to the radius. In an airplane, you can see a distance expressed in miles approximately equal to the square root of 1.5 times your height expressed in feet. Now this is not the Pythagorean theorem. This is an old airplane pilot rule of thumb. Here we are on the ground, and you can see our altitude there. It's going up. And look into the distance. You can see the land beginning to appear. We're at 4,000 feet. We can see more and more and more into the distance because we can see further and further. The horizon line is where the curvature of the Earth makes the Earth invisible beyond that point. Well, nothing new there, but we're looking down and we can see further and further. If you are 6 feet, you can see about 3 miles because 1.5 times 6 is 9, and 3 times 3 is 9. If you are in feet, you can see in miles about the square root of 1.5 in. If you are at 600 feet, you can see about 30 miles because 1.5 times 600 is 900. And 30 times 30 is 900. This is just a rule of thumb. It works every time, but it's not as good as the Pythagorean theorem. Engineers and airplane pilots, they are full of rules of thumb. They avoid mathematics whenever they possibly can. Well, a calculator is fine and dandy, but a spreadsheet is better. And with spreadsheets, you can set up the problem once, then merely change the variables. And now I'm going to go off of the slide presentation and go to the spreadsheet. And that is a separate video that I'm going to tack on to the tail end of this one. In this portion of the presentation, I'm going to use a spreadsheet, and a spreadsheet has some advantages over a calculator in that once you set it up, you can just change your variables and use it as a device to analyze the data more easily. I'm going to put my information down the column and across the top. First thing we're going to look at is how high is your eye off the ground, and then the radius, and then the hypotenuse. Now, if you look over at the picture, our radius is the distance from the surface of the Earth to the center. And that's going to be in miles 4,000. The hypotenuse, the longest leg of the triangle, consists of the radius plus your height off the ground. Well, your height off the ground in feet is going to be 6. So the hypotenuse is going to be 6 feet plus 4,000 miles. Now that 6 feet is not much. Let's convert the 6 feet to miles over here. And I'll put equal 6 divided by 5,280. And that's going to be a very small fraction. And the hypotenuse is just going to be those things added together, the radius plus your height off of the ground. Not much difference. Over here, I'm just going to square everything. And we're going to square the radius and the hypotenuse. So let's take C3 times C3 down here. We're going to label this the component that you can see. That's the horizon line. That's going to be from here where it touches the ground to your eye. And in this case, my eye is 6 feet off of the ground. And that's what I want to compute. Well, I have squared the radius. Why don't I square the hypotenuse? I'm just going to copy this, paste. Now, in order to get this component, the square of this component, what I can do is take the square of this component, the hypotenuse, and subtract the square of the radius. And that's going to give me the square of this line. So I will put down equal D4 minus D3. In order to see how far I can see, I'm just going to now take the square root of that. And that's how far you can see when you are at 6 feet with the diameter of the Earth being 4,000 miles. We can now alter this 6-foot figure, and let's change it to 600 feet. Oh, it didn't change. What happened? Oh, because I put in 6 here. Instead of putting in 6, I should be putting in B2. At 600 feet, you can see 30 miles. At 6,000 feet, you can see 95. Now we can actually pose the question, how far can you see on the moon? Well, you're wearing a spacesuit and you're 6 feet off the ground. The diameter of the moon is 2,000 miles. The Earth's diameter is 8,000 miles. So the radius of the moon is 1,000 miles. You can only see 1.5 miles on the moon while standing. So you could get lost very, very easily walking around on the moon. Plus, there is no fog or haze from air, and things look startlingly clear in the distance. And you could actually be 2 miles from your moon base, be walking around and not see it. On Earth you would see it because you can see 3 miles. In order to be able to see 3 miles on the moon, you'd have to be standing on something. You'd have to be 24 feet in the air in order to see 3 miles. The Pythagorean theorem says that if you square the radius, square the other component, those two squares will be equal to the area of the square of the hypotenuse. Then you can take a square root of the hypotenuse to calculate this line.